welcome back, and I'm back with servos again. What I've got now is, and I kind of had it before but I've more or less perfected it now, is a position and a speed control all combined into one. So if you can remember in the old days, in the analog days, if you wanted a speed controller you would have a tacho on the feedback. So here's a motor, and you'd have a tacho here which measured, which is just like a DC generator which would measure the speed. And if you wanted a position control, you would have had a potentiometer on here, and it would have gone plus or minus, I don't know, 90 degrees or less, and you would only be able to swing back and forward a certain angle. But now with our quad detectors that we've got, this one's got 4096 pulses in a revolution of the shaft. We can measure the speed as well, but I'm not actually using it in that. I mean, I could actually differentiate this signal, and that would give me velocity, but that's not a very good thing to do because it's very kind of noisy anytime you differentiate anything. So what I've done instead is I've just designed a position controller where I've put very high gain into it, and like two integrators. One of the integrators is already there. It's a mechanical integrator, which is caused just by measuring. If you measure position, that gives you an integrator, really, just like with a potentiometer. You've got a 1/s term in the loop, so it's the same thing. So I've got that, and because it's a type 2 system, I've got two integrators. It means I can follow a ramp very easily. But before I do that, just let me show you this before we go into any theory. So this is it's using the FPGA to do everything, really, because I get much better results from the FPGA. So here's my set point. So at the moment that's position servo, and you see how fast it is as well, because I've got a bandwidth of 100 Hz, which is quite high for a kind of old motor like this. It's a bicycle motor, but it's not intended to be a servo by any chance. It's just bought off eBay type thing. Controlled by a myRio, and this key element here, the H-bridge, is the 100 amp one, which is used just as a safety thing. I don't really need 100 amps, but when I'm experimenting and the thing goes into oscillation or something, you can blow up the other one, so it's good to have a really powerful H-bridge so you don't have to keep replacing it. But the thing about this is, now we can, if we put a ramp into this system, we'll get a velocity controller. So here's our front panel, our VI, and what I'm going to do is just put in my velocity profile. You'll see I say velocity, I mean speed, of course. 100 RPM there I've selected. You'll see that the sensor's going to 100. That's calculated in the FPGA as well. The position's going mad because it's going round and round now. And you'll see that it's now becoming a speed controller. And that is going to stay quite steady there, even though I try and stop it. Now if I click this button here, I can hold it in a position, so I've held it, and then I can go back to position control. So I can just stop at any time and I've got position control, let it go, and I've got speed control. I've got both combined, and the reason you can get away with this, of course, is because of that sensor goes round past 360, which you can't get in an analog system, and you can't have a ramp that goes up forever, of course. Now the ramp here is just a counter that counts up. It's 64 bits, it needn't really be 64 bits, but 64 bits running at 1000, if you've got a 1000 RPM motor with 4096 pulses on it, you have a very long wait before that integer overflows. Anyway, so here's our phase advance, which I've set it to 100 Hz. It's a very high gain, 4000, and I've got two phase advances, although it says one there. I've actually got, sorry, two phase advances here set at 100 Hz, and this is just our integrator PI. It's not really an integrator. It's it's really a phase lag compensator that I can put pure integration there. Okay, it doesn't make a huge amount of difference because it's very low frequencies that goes in, but there we go, that's with the pure integrator. But nevertheless, I can't stop this very easily at all. If I try and physically move it, it's very hard, and that's all current. There's no gearbox in there holding it. Also makes it very fast as well. So how does this work? I mean, how does gain keep the thing in place? So if you think of a very simple integrator, there's its Bode-plot. There's our bandwidth, it's where it crosses unity gain. It's got a phase shift of -90 degrees. At a particular frequency down here somewhere, where I'm trying to, let's say I'm putting some disturbance in here, it's got a set amount of gain there to reject that disturbance, to reduce the error. And the slope is -20 dB per decade. But clearly if I could get that higher, I could get more gain and reject more disturbance. But what I could do is just increase the gain. Well, what that would do is that would increase the bandwidth. That would be good, that would make it faster, and I'd get more gain. But there's a couple of problems with that, mainly at high frequencies there's all sorts of nasties waiting to get you in oscillations and things. So if you just increase the gain on its own, it's not really such a smart thing to do. But you can sort of modify that and say let's attenuate the high frequencies. Well, that's a little bit better. You're still limited here with the slope of this as to how much gain you're going to get down here. Phase characteristic changes, as you can see. It goes down to -180. So our phase, we would lose a little bit of phase margin. There's our phase margin where it crosses over unity gain. So rather than being 90 degrees, it's a little bit less. Then what we can do is probably the ultimate is not that one. This one here is that's nearly the ultimate. Put two integrators down at low frequencies. There's already one there already. Put a second one in, and then you get this really steep slope, -40 dB per decade. Well, now at some frequency here, let's say that you put a disturbance in, rather than having that kind of gain, it's got this amount of gain. It's much higher. And of course, if you could make that even steeper, you could put like a third integrator, but that's not really practical because it affects the phase. So we've got something like that. But again, in practice, we don't do that because we want to roll off at high frequencies. So we normally do something like this. So -40, -20 through unity gain, and then -40. And we get this really nice phase advance, sort of goes to a maximum and the minimums. You've got to get the gain right here so that it crosses over at, let's say, 100 Hertz. If you don't, then the phase margin you'll easily notice because it starts to oscillate or get to overshoot and so on. Okay, so that's pretty good. But what I've done is one stage further. I've added a second phase advance to get even more phase, and really this comes down and kind of goes flat. Asymptotically it goes flat, but in real life it sort of sneaks through. Hopefully you only want one unity gain crossing, otherwise there's problems there as well. But I've actually got something more like this, which is not quite two integrators because I knocked out my pure integrator and I've got this. So this is a lag lead. It's got a lag at low frequencies and then a lead at unity gain, but I've got two leads rather than one, but it's kind of like that. So you've got this gain is quite high. Let's say some frequency here is very high. If you put two integrators, you get even more gain, but you don't gain a huge amount. But with two integrators, you should be able to follow without any error a ramping input. This is a classical control stuff. They talk about ramp error coefficients and so on. So you've got two integrators, but if you've got close to two integrators, you can do the same thing anyway. You just don't get quite zero error. So that means that you can put a ramp into the position controller and you've got yourself a speed controller. And if you stop it at any time, you've got a position controller. So you've got a position and a speed controller all combined into one. And as I said before, let's turn the speed down. I'll turn it back on again. That's onto speed control. You can see it going around. I'll turn it down so it goes off. So it's just purely position control now. This torque that's holding it, I can try and, you can see the current trying to go up. It goes quite high, and because the current is, it needs current to create torque. So when I introduce the disturbance, it's drawing more current to keep the position in the right place. And that's all integrators that's doing that. And phase advances, it's keeping it stable. So that's why I can do this. And if my stability is not right, of course I can adjust it and so on. So that's a demonstration of position servo running off the FPGA, mostly off the FPGA, and a speed controller all combined into one. Something that you probably wouldn't have been able to do in the analog days unless you used a thing called a synchro and an AC system, which is a little bit different. In military control systems they probably did do something like this, but in the analog domain maybe. But this is rather interesting that you don't have to treat the two subjects as separately. It used to be in textbooks you look at position control, you look at speed control, two separate things. As long as you have a couple of integrators in there, you can track a ramping input. Both can be one, and you only need the one sensor as well, so you don't need a tacho like you used to in the old days. You don't even need to differentiate the signal from there to get speed, because we just put a ramp in instead. And the ramp is never ending, it can go on for, well, indefinitely. Okay, so I hope that helped, a bit of understanding of servos. It's all down to gain, high gain at low frequencies, low gain at high frequencies, as big a bandwidth as you can squeeze out of it. You can see I've got 100 Hertz bandwidth set on the phase advance. And really the design is all about pushing it up higher and higher and higher. 100's pretty high for a motor like this. Thank you very much. Bye bye.